Hey guys, my name is Willow, and today I'm going to be explaining how to do limiting reaction stoichiometry as a part of my extra credit project. So before we begin 2 examples, let's go over the 5 steps that you need to follow in order to complete the stoichiometry problem. So first off, you need to have a balanced equation. And this is important because later on when you have to make a mole ratio, you're going to look at the coefficients of each of the products and reactants, so it's very important that you balance the equation right. Next, you're going to convert to moles with reactants. So basically, you're going to find the molar mass of both of your reactants and convert to moles, and this way we can determine the limiting reactant. And this might be new if you're just beginning limiting reactant stoichiometry, but I'm going to help explain how I think about it, so hopefully that can help you. And then our next step is going to be mole ratio, and this is a very crucial step when you are doing stoichiometry, and it's basically what defines a stoichiometry problem is that you absolutely have to have a mole ratio. And then our final step is going to be convert to the units you ask for. So if you remember this, when you're doing other types of stoichiometry problems, later chapters such as gas stoichiometry or solution stoichiometry, you'll remember to convert to pressure, for example, instead of leaving it as moles. Okay, so let's look at our first example. I have the problem written down. It says a solution made of 25 grams of zinc chloride is reacted with a solution made using 25 grams of lithium hydroxide. What will be the mass of each product and reactant when the reaction is complete? Okay, so the first thing we need to do is write a balanced equation. So this would be ZnCl2 because of the charge of zinc, and this is aqueous, so we know that because it says solution, is mixed with lithium hydroxide. Those both have a charge of 1, and this is a double replacement reaction, so it's going to create zinc hydroxide, charge of 2 again, and lithium chloride. And this is, both of the products are going to be aqueous because it's a double replacement. And so this is unbalanced because of the 2 here. So I'm gonna put a 2 here and a 2 here. And that should be good. Okay, the next step in our process is convert to moles using the reactants. So in the problem, it tells us that we have 25 grams of each of our reactants, but we have to convert to moles because we cannot just look at grams when solving for a limiting reactant, because even if it's 1-to-1, in this case it's not even 1-to-1, but you always have to convert to moles. So you're going to divide by the molar mass. And so if you want to think about this in a dimensional analysis way, you just put what you know over 1, and then I went ahead and did the molar mass already, so this would be 136 and this would be 24. And so then there's 136 grams in 1 mole, 24 grams in 1 mole of each of these reactants. And then when you do that division, over here you get 0.183 moles, and over here you get 1.04 moles. Now, if you're thinking to yourself, I'm just going to take whatever is the smaller mole value, that's not going to work in this case because you do not have a 1-to-1 ratio. And so how I like to think about determining the limiting reactant, I do this every single time for any chapter, and it's always worked. Basically, you're going to put both of the moles that you have over 1, set up another dimensional analysis, and then you're going to look at the coefficients of each of your products and kind of compare them to a coefficient of the coefficients of both of your reactants and compare them to one of your products. So for in this case, we have a coefficient of 1. I didn't write it, but so you're going to put the 1 down here and then compare it to the 1 here. Same thing on this side. You have a coefficient of 2, so you put the 2 down here and the 1 up here. So now, when you divide out 1.04 divided by 2, I don't have the exact calculation, but this is going to be around, whatever this is, it's still not going to be bigger than this. So the way that I like to think about it is you compare it to another coefficient, and then you always go with which one's smaller. So this is like a foolproof method that I use. So say I did this division, it's like 0.5 something, it's still not going to be smaller than this molar mass. And since this is 1-to-1, you don't have to do any division. So you always go with one smaller after you compare. So in this case, I just found my limiting reactant, so you can check off the first 3 steps. Okay, so now I'm going to talk about using an ICF table. ICF stands for Initial Change Final. And so you're going to put the initial value of the limiting reactant. So this would be 0. So basically you're going to have 4 different sections, and they're going to compare it to each of your products or reactants in each of your products. So the initial value that you have for zinc chloride is 0.183. The initial product that you have over here is 1.04 right here. And then you don't have anything made yet because the product hasn't happened, or the reaction hasn't happened. So this is a 0. And then you're going to add subtraction signs and plus signs because when the reaction's happening, you're taking away from the reactants and adding to the products. Okay, so now, because we determined our limiting reactant, we're going to carry it down. I like to put parentheses. We're going to do 0.183, 0.183 for every single one. Again, this is our limiting reactant. And now we're going to put more parentheses because we have to determine our mole ratio. And so a mole ratio is a ratio between the coefficients. So for example, our limiting reactant right here, our mole ratio would be 1/1 because you're comparing the limiting reactant to itself. Over here, it's going to be 2/1 because the limiting reactant is always on the bottom. Sorry, I forgot to mention that. And then the coefficient up here is a 2. So then you can put 1 on the bottom of all of these because that's the limiting reactant coefficient. And so over here, it's going to be a 1/1. Over here, it's going to be a 2/1. So we're just putting the limiting reactant on the bottom and then comparing it to the coefficients of everything else. Finally, our F stands for final. So you're just going to do this math. And I like to start with the limiting reactant because you can kind of check your work and see if you get a 0. Because if it's the limiting reactant, it should be used up in the process. So you're going to get a 0 grams as your final answer. Okay, over here, when you do the math, 1.04 minus this times this, you're going to get 0.674 moles. When you do the math over here, 0 plus blah, 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 you're going to get 0.183 moles. And when you do the math over here, 0 plus this, you're going to get 0.366 moles. Okay, so now we are not done because we have to convert to units like it says in our last step. And so again, we're going to divide by the molar mass of each product. So we already calculated this was 24. So you divide by 24, and you're going to get 16.2 grams as your final answer for this reactant. Excuse me. And then over here, the molar mass is 99.4. So you're going to divide by that, and you'll get 18.2 grams. And then over here, you're going to divide by 42.4 to get 15.5 grams as your final answers. Okay, we're going to look at one last example now. This one's a little bit more simpler. So the question says, what will be the mass of the precipitate when 15 grams of calcium acetate is used to make a solution, and that solution is combined with a solution with 25 grams of sodium carbonate? And the question sounds a little bit confusing, but I didn't write it. Mr. Simcoe did. I just pulled it off of a review sheet. But basically, this is just a complicated way of giving you your phase symbols. So let's start by writing our balanced equation. I rewrote the steps down here. So calcium acetate, calcium is a charge of 2, and this is going to be an aqueous, of course, is combined with sodium carbonate. Okay, and this is used to make, we know we're going to have a precipitate, which is another word for solid, and we know that we're going to have another solution. So first we have our sodium acetate, and then we have our calcium carbonate. And so now we have to refer to our solubility rules to determine which is going to be the precipitate and which is going to be the aqueous solution. So because this is a group 1 element, and also acetate is just one of the ones on the solubility list, this is going to be our aqueous solution, and this is going to be our precipitate. Okay, so the next step in our list is to convert to moles using the reactants. So over here we have 15 grams, and over here we have 25 grams. Okay, so now we have to divide by our molar mass to get it into moles. I went ahead and did that already, so it's going to be 0.95 moles here, or sorry, 0.095 moles here, and 0.236 moles over here. And so now, if we think about what we did in the last problem, we set up a little dimensional analysis problem so we can see which one is our limiting reactant. Oh wait, sorry, I forgot to put a 2 here, but this needs to be balanced, sorry. And so because it's a 1-to-1 ratio here, there's no coefficients, the problem would look like this. And so when you're gonna have the same answers anyways. So now you can look at which one is smaller, and that's going to be this one. So calcium acetate is going to be our limiting reactant. Okay, so now that we have that, we did our dimensional analysis, found the smaller value, we have to do a mole ratio. And so we're not going to do an ICF table in this problem because we're only asked for the mass of the precipitate. An ICF table was useful when we were asked for the mass of every product and every reactant, but we're only looking for the precipitate. So we're just going to refer to good old dimensional analysis. So we put what we know for one, and what we know is the moles of the limiting reactant. And we're always going to start with our limiting reactant because we don't need our excess. We want to know what's running out, so we're going to look at the limiting. Okay, and so now we're going to do the next step, mole ratio, of course, 1-to-1, because we're looking at the precipitate, not the aqueous solution. So look at this one versus this one. And then we need to convert to the units that we're asked for, and so we're asked for the mass, so we need to find grams. And so we're going to multiply by the grams of our calcium carbonate, which would be 100, to get 9.5 grams of calcium carbonate. And that's our final answer because we're only asked for the mass of the precipitate. So I hope this could help you, and yeah, thanks for watching.